Now here the question is, draw the graph of fx equals sine inverse of mod sine x plus cos inverse of cos x. Find the range of the function. Find the points of non-differentiability. Also, find the value of this integral from 0 to 10 pi sine inverse of mod sine x plus cos inverse of cos x dx. Now we are given this function fx, which is sine inverse of mod sine x plus cos inverse of cos x. Now, period for this function is pi and fundamental period for this second function is 2 pi. So this function fx, it is periodic with the period 2 pi. Now what we'll do is, we'll write the definition of fx between 0 to 2 pi, we'll draw its graph and then we'll generalize the function. Now we'll recall the graph of sine inverse of mod sine x. We know that this graph is from 0 to pi by 2 x, from pi by 2 to pi it is minus x plus pi, from pi to 3 pi by 2 it is x minus pi, and then from 3 pi by 2 to 2 pi it is minus x plus 2 pi. So this is the graph of y equals sine inverse of mod sine x. Now we'll draw the graph of cos inverse of cos x. It's a very standard function. So this is 0, pi and 2 pi. Now between 0 to pi it is x, and between pi to 2 pi it is minus x plus 2 pi. Now we'll write definitions for this function fx. Now first definition is when x lies between 0 to pi by 2. Between 0 to pi by 2, both the definitions, they are x. So it will be simply 2x. From pi by 2 to pi, here the definition is minus x plus pi, and here it is plus x. So we'll add them, we'll get this as pi. Between pi and 3 pi by 2, definition here is x minus pi, and here the definition is minus x plus 2 pi. So we'll add them, we'll again end up getting this value as pi, and then between 3 pi by 2 and 2 pi, this is minus x plus 2 pi, and it is also minus x plus 2 pi. So it will be 4 pi minus 2x. So we can write this function fx as 2x when x lies between 0 and pi by 2. It will be pi between pi by 2 and 3 pi by 2, and then we have 4 pi minus 2x when x lies between 3 pi by 2 and 2 pi. Now we'll draw the graph of fx. We'll draw the axis. Then we'll mark the points on axis. So this is pi by 2, pi, 3 pi by 2 and 2 pi. Here also let it be pi by 2 and let it be pi. Now first is y equals 2x. When x is 0, it is 0, and when x is pi by 2, it is pi. So we'll draw this graph. Now between pi by 2 and 3 pi by 2, this value is pi. Now between 3 pi by 2 and 2 pi, if we'll put x as 3 pi by 2, we'll get this as pi. And we'll put x as 2 pi, we'll get this result as 0. So between 3 pi by 2 and 2 pi, it will be simply this straight line. So that is the graph of this function fx, which is sine inverse of mod sine x plus cos inverse of cos x. Now this graph will repeat in the same fashion. So this is how we can draw the graph of sine inverse of mod sine x and cos inverse of cos x. Now as you can see, this function is continuous in x belongs to R, but it is not differentiable at pi by 2, 3 pi by 2, 0, 2 pi. So it is not differentiable at odd multiple of pi by 2 and at 2n pi. So it is not differentiable at x equals 2n pi and 2n plus 1 pi by 2. Now we need to find range of this function also. So range of this function is from 0 to pi. As we can see, this graph, it lies entirely in this interval from 0 to pi. So range of this function, it is from 0 to pi. Now we need to find the value of this integral from 0 to 10 pi fx dx. Now since this function is periodic with a period 2 pi and 10 pi is a multiple of 2 pi, we can simply write this as 5 into 0 to 2 pi fx dx, and this integral from 0 to 2 pi fx dx is nothing but area under this trapezium. So we can simply write this as 5 and then 1 by 2. Now sum of lengths of parallel sides. Now this is 2 pi and this is 3 pi by 2 minus pi by 2, which is simply pi, and then this height, which is also pi. So this area, it will be 5 by 2 into 3 pi square. So it will be 15 pi square by 2. So value of this integral will be 15 pi square by 2. Discuss the differentiability of the function y equals mod of 1 minus mod of 1 minus mod of 1 minus mod of 1 minus x. So we'll draw the graph of this function, and from the graph we'll work out differentiability of this function. So my basic graph here is y equals 1 minus x, which is a straight line. So when x is 0, y is 1, and when y is 0, x is 1. So that is the graph of y equals 1 minus x. Now I'll take the transformation of y equals mod fx. So mod of 1 minus x. Now transformation of mod fx is mirror on x-axis, take the reflection of down on up, and then erase the graph from third and fourth quadrant. Now I'll take the transformation of y equals minus mod of 1 minus x. So transformation of minus fx is rotate the graph 180 degrees about x-axis. I'll take the transformation y minus 1 minus mod of 1 minus x. So I'll need to shift the graph plus 1 units along y-axis. Now next again, I'll take mod fx, so which is 1 minus mod of 1 minus x. Now again I'll take the transformation. Then again I'll shift it. Now again from here, y equals mod of 1 minus mod of 1 minus mod of 1 minus x. So minus 1, 0, 1, 2 and 3. Now we'll just need to do that one more time. And then finally, transformation of another mod of x. So this is minus 2, minus 1, 0, 1, 2, 3 and 4. Now it is continuous for x belongs to R, but it is not differentiable at these points. So it is not differentiable at -2, -1, 0, 1, 2, 3 and 4. Discuss the continuity and differentiability of the function fx equals greatest integral function of x sine pi x when the value of x lies between -1 and 1. So what I'll do is I'll draw the graph of y equals sine pi x. So I'll draw the graph of sine x. Now for sine pi x, I'll divide every value with pi. So now here it will be -1, 0 and this one will be +1. So I'll take two separate cases. Case 1, when the value of x lies -1 and 0. When x lies between -1 and 0, in that case, the value of sine x will also lie between -1 and 0. So here I can say the value of sine pi x will also lie between -1 and 0. Now if I'll multiply them, then when I'm multiplying two negative numbers, I'm bound to get a positive number. And because numerically their value lies between 0 and 1, so still their product will also lie between 0 and 1. So this value will lie between 0 and 1. So if I'll take their greatest integral function, so I'll write x sine pi x, this value will always be 0. So when x lies between -1 and 0, the value of greatest integral function of x sine pi x is 0. Now I'll take the second case. Now second case, when the value of x lies between 0 and 1. So when x lies between 0 and 1, the value of sine pi x, it will also lie between 0 and 1. So it will lie between 0 and 1. Now if I'll multiply it, I'll get this value as x sine pi x will always be greater than or equal to 0, but less than 1. It will be less than 1 because in order to achieve the value 1, for both of them, they have to be 1 simultaneously. But they are not 1 simultaneously at one point. So this value will always be less than 1. So in this case also, greatest integral function of x sine pi x is 0. So the given function fx in the interval -1 to 1 is nothing but a constant function which is 0. And any constant function in an open interval is both continuous as well as differentiable. So answer is this function is continuous and differentiable in -1 to +1. Now the question is, we are given this function fx which is x into e to the power -1 upon mod x plus 1 upon x when x is unequal to 0, and it is 0 when the value of x is 0. Now we have to test its continuity and differentiability at x equals to 0. Now if we look at its left hand limit, it will be f0 negative, and we can write this as limit h tends to 0, and it will be this minus h e to the power -1 upon, now mod minus h is plus h, and here will be this 1 upon minus h. Now plus h and minus h will cancel, so this is e to the power 0 which is 1, and 1 into 0 is 0. So left hand limit is 0. Now we'll find its right hand limit. It will be this limit h tends to 0. Now this is h e to the power -1 upon h plus 1 upon h, which is this limit h tends to 0, h into e to the power -2 upon h. Now this is 0 into e to the power -infinite, which is also 0. So this is 0. So for this function, f0 negative is equal to f0 positive, and it is equal to f0. Therefore this function is continuous at x equal to 0. Now we'll test its differentiability. Now f dash 0 negative, it will be this limit h tends to 0. Now f minus h will be this minus h e to the power -1 upon h minus 1 upon h
minus f0 upon minus h. Now this minus h and minus h will cancel, and this h and h will also cancel. So this is e to the power 0, and e to the power 0 is 1. So left hand derivative of this function at 0 is 1. Now we'll find its right hand derivative. It will be this limit h tends to 0. Now this is h e to the power minus 1 upon h plus 1 upon h minus 0 upon h. Now this h and h will cancel, and this is this limit h tends to 0 e to the power minus 2 upon h, which is e to the power minus infinite, and e to the power minus infinite is 0. In this case, left hand derivative is not equal to right hand derivative, and therefore this function is not differentiable at x equal to 0. So it is continuous but not differentiable at x equals 0. Now here the question is, we have defined this function fx as minus 1 when x is less than 0, and this is x minus 1 when x is greater than 0, and gx is f mod x plus mod fx. Now what we'll do is, we'll draw the graph of fx. Now between minus 2 and 0, this is minus 1, and at 0 this is minus 1, at 1 this is 0, and at 2 it is 2. It is a continuous function, so we may include 0 at any point. Now this is minus 1, and this is x minus 1, and this point it is 1. This is 2, and this is minus 2. Now first we'll draw the graph y equals f mod x. Now for mod x transformation, we'll erase the graph from second and third quadrant, and then we'll take the reflection of right on left. So this f mod x graph, it will be this graph and this graph. Now this is x minus 1, and this is minus x minus 1 in between these values, and its definition changes at 0. Now if we look at y equals mod fx, we'll take the reflection of down on up and erase the graph from down. So now this graph, it will be now this is 0, this is 1, and this is 2. This is plus 1. This is minus x plus 1, and this is x minus 1. Now we'll start writing the definition of gx. Now when x lies between minus 2 and 0, this definition is minus x minus 1, and this is plus 1. If we add them, it will be simply minus x. Now in between 0 and 1, this is x minus 1, and this is minus x plus 1. So it will be 0. And when x lies between 1 and 2, it will be 2x minus 1. Now this function is clearly continuous. Now we find g dash x. G dash x will be minus 1 when x lies between 2 and 0. This is 0 between 0 and 1, and this is 2 between 1 and 2. Therefore it is not differentiable at 0 and 1. So this function gx, it is not differentiable at x equals 0 and 1. And that is the answer to this question. Now here the question is, we are given this function fx as x cube minus x square, and I think here it should be this plus sign. Plus x plus 1, and gx is max of ft when x lies between 0 and 1, and it is 3 minus x when x lies between 1 and 2. Now we look at this f dash x will be 3x square minus 2x plus 1. Now d in this case will be 4 minus 12, which is less than 0. That means this is always greater than 0. So this fx is an increasing function. Now if fx is increasing, then in this interval between 0 to 1, for any t which lies between 0 to x, maximum value of this function, it is going to occur at fx. So this entire definition, it is nothing but it is simply fx. So now we can write this gx as x cube minus x square plus x plus 1 when x lies between 0 and 1, and it is 3 minus x when x lies between 1 and 2. Now we need to find its continuity and differentiability in 0, 2. Now g1 negative is equal to g1, and it will be 1 minus 1 0, and it will be 2, and g1 positive is 3 minus 1, which again is 2. Now if we find g dash x will be 3x square minus 2x plus 1 when x lies between 0 and 1, and it is minus 1 when x lies between 1 and 2. Now here we can write g dash 1 negative as 3 minus 2 plus 1 will be 2, and g dash 1 positive is minus 1. So this gx, it is not differentiable at x equals 1. So in this interval it is continuous, but it is not differentiable at x equals 1. Now here the questions. We need to discuss differentiability of this function at x equals to e. Now it is given that this fx is x minus e to the power 1 upon e minus x. Now we'll check its continuity first. So we'll write f e negative as this limit h tends to 0, and then we'll write x as e minus h. So it will be this minus h into 2 to the power minus 2 to the power 1 upon minus h. Now this is 0 into, now this is 2 to the power minus infinite. 2 to the power minus infinite is 0, and 2 to the power 0 is 1. So its left hand limit at e is 0. Now right hand limit at e, it will be this limit h tends to 0. Now this is e plus h. Now we can write this as h into 2 to the power minus 2 to the power 1 upon 1 by h. Now this is 2 to the power infinite, which is infinite, and 2 to the power minus infinite is 0. So this is 0 into 0. This again is 0. And we are also given that f equals 0. Therefore, this function is continuous at x equals e. Now we have to check its differentiability. Now if we find f dash e negative, it will be this limit h tends to 0. Now f e minus h will be this minus h 2 to the power minus 2 to the power minus 1 upon h minus 0 upon minus h. Now this minus h will cancel. Now this is going to be 2 to the power minus infinite 0, and 2 to the power 0 is 1. So this is 1. And if we find its right hand derivative, it will be f dash e positive, which is limit h tends to 0. Now it will be this h 2 to the power minus 2 to the power 1 by h minus 0 upon h. Now h and h will cancel. Now this is 2 to the power infinite. 2 to the power infinite is infinite, and 2 to the power minus infinite is 0. So in this case, left hand derivative is not equal to right hand derivative. Therefore, this function fx is not differentiable at x equals e. And that is the answer to this question. Now here the question is, discuss the differentiability of the function fx equals sine inverse 2x upon 1 plus x square. Now we have solved n number of questions like this in inverse trigonometric function. So here what we need to do is, we need to split the definition according to the values of x. Now for this, what we'll do is, we'll let x as tan theta, and if x is tan theta, then theta is tan inverse of x. Now principal value range of tan inverse of x is from minus pi by 2 to plus pi by 2. That means value of theta is going to lie between minus pi by 2 and plus pi by 2. Now if we put x as tan theta, this fx, it will be sine inverse, and this is 2 sine theta upon 1 plus sine square theta, which is sine 2 theta. So here we have sine inverse of sine 2 theta, where this angle 2 theta, it will lie between minus pi and plus pi. Now we have to use self-adjusting property of sine inverse, and for that we'll use the graph of sine inverse of sine x. Now graph of sine inverse of sine x, it is drawn like this. This is 0. This is pi by 2, minus pi by 2, minus 3 pi by 2, and this is 3 pi by 2. Now when x lies between minus pi by 2 to plus pi by 2, this is simply x. We are talking about sine inverse of sine x. Now between pi by 2 and 3 pi by 2, this is minus x plus pi, and here slope is downward, so this is minus x, and this point is minus pi, so it will be this minus x minus pi. So depending on value of 2 theta, we'll have 3 separate intervals. So it will be minus pi minus 2 theta when 2 theta lies between minus pi and minus pi by 2. Now when 2 theta lies between minus pi by 2 to plus pi by 2, it is simply x, which is 2 theta, and when 2 theta lies between pi by 2 and pi, in that case it will be pi minus x, which is pi minus 2 theta. Now theta here is tan inverse of x, so we can write this as minus pi minus 2 tan inverse x, and this is when theta lies between minus pi by 2 and minus pi by 4. So this is minus pi by 2, and theta is tan inverse of x, and this is minus pi by 4. Now this is 2 tan inverse of x, and here theta will be between minus pi by 4 and plus pi by 4, and this is pi minus 2 tan inverse of x when tan inverse x, we have already included pi by 2 here, we'll discard it here, so it will be less than, and then tan inverse, and this is pi by 2. Now we take tan, this is minus infinite, which is always true, so we'll get x is less than minus 1. This is when x lies between minus 1 and plus 1, and this is when x is greater than 1. So sine inverse of 2x upon 1 plus x square, it can be expressed as minus pi minus 2 tan inverse of x when x is less than minus 1. It is 2 tan inverse x when x lies between minus 1 and plus 1, and it is pi minus 2 tan inverse of x when x is greater than 1. Now let it be this function fx. Now f minus 1 negative, it will be minus pi minus 2, and tan inverse minus 1 is minus pi by 4, so it will be this minus pi by 2, and f minus 1 equals f minus 1 positive, it will be 2 into tan inverse minus 1, which is minus pi by 4, which is minus pi by 2. That means this function is continuous at minus 1, and at 1 f1 negative is 2 tan inverse 1, and tan inverse 1 is pi by 4, so it will be this pi by 2, and f1 positive, it will be pi minus 2 tan inverse 1 is pi by 4, so it will be this pi by 2, and f1 is also this value. So it is continuous at x equals to 1. So this function fx, it is continuous in x belongs to R. Now if we find f dash x will be minus 2 upon 1 plus x square when x is less than minus 1, and it will be 2 upon 1 plus x square when x lies between minus 1 and 1, and again it will be minus 2 upon 1 plus x square when x is greater than 1. Now left hand derivative f dash minus 1 negative, it will be minus 1, and f dash minus 1 positive, it will be plus 1. So it is not differentiable at minus 1. In the same way, f dash 1 negative, it is 1, and f dash 1 positive, it is minus 1. So it is not differentiable at 1. So this function sine inverse of 2x upon 1 plus x square is not differentiable at x equals minus 1 and x equals plus 1. Now here the question is, we are given this function which is y and x, and it is given by x square plus x square upon 1 plus x square up to x square upon 1 plus x square to the power n minus 1. Now clearly for this function, x square is continuous and differentiable in R, and 1 plus x square is also continuous and differentiable in R, and 1 upon 1 plus x square is also continuous and differentiable in R. So this yn, it is continuous and differentiable in x belongs to R. Now this y-axis, this limit n tends to infinite y and x. Now this y and x, it is actually a GP, and here we are talking about sum of infinite GP. Sum of this infinite GP will be a upon 1 minus r, and r in this case is 1 upon 1 plus x square. So it will be this x square into 1 plus x square upon x square, provided x is unequal to 0. And if x is 0, then this y and 0, it will be 0. In that case, this function yx will be 0. So this yx is 1 plus x square when x is unequal to 0, and ab 0 at x equal to 0. Now clearly, left limit and right limit, they are both 1, and value at 0 is 0. This function is discontinuous at x equals 0. Now here the questions, we are given this function fx, which is p square minus 1 into greatest integral function of tan inverse x plus 4 into, now we'll add 1 and subtract 1. So it will be this q plus 1 whole square minus 4 into fractional part of 1 upon 2 plus x square and plus p plus q signum of x square minus x plus 2. That says it is continuous in R, and fx1 equals fx2 for all x1 and x2. Then the largest value of mod p plus q is. Now it is continuous, and fx1 equals fx2 means it is a 1-1 function. And if it is 1-1, then it is either always increasing or it is always decreasing. Now if we look at this, x square minus x plus 2, d in this case is 1 minus 8, which is less than 0. That means it is always positive, and if a function is always positive, then its signum value is always plus 1. So this is always plus 1. Now if we look at this tan inverse of x, then we know that this is the graph of tan inverse of x. It goes from plus pi by 2 to minus pi by 2, and if we take integral value here, this is 1 and this is minus 1. So this function, it will be discontinuous at minus 1 and plus 1, but it says, but the question says this function is continuous in x belongs to R. So if it is continuous in x belongs to R, then this p square minus 1, it must be equal to 0. So this coefficient, we'll put it equals to 0. So p square minus 1 equals to 0, which means value of p is either plus 1 or minus 1. Now if we look at 1 upon 2 plus x square, then if we take y as 1 upon 2 plus x square, now we know that x square will always lie between 0 and infinite. Now 2 plus x square will always lie between 2 and infinite, and if we take reciprocal, then 1 upon 2 plus x square will always lie between 0 and 1 by 2. And if it lies between 0 and 1 by 2, then fractional part of 1 upon 2 plus x square will be 1 upon 2 plus x square. So now we can write this function fx as 4 into q plus 1 whole square minus 4 into 1 upon 2 plus x square plus p plus q. Now this function 2 plus x square, it is a minimum function. So if this term exists, then this function, it cannot be 1 1. So it will be 1 1 only if this expression is 0. That means q plus 1 whole square equals 4 or q plus 1 equals plus or minus 2. Value of q is either 1 or minus 3. Now we have to find the greatest value of mod p plus q. Now this value will be greatest when this p is minus 1 and q is minus 3. Then this greatest value will be 4. So answer to this question is this option C. And this question we are given this function fx and it says this function is continuous in minus 2 to plus 2. Then we need to find the value of f minus 1 by 2. Now what we'll do is we'll write definition of this function fx. Now we know that fractional part of x plus greater function of x is simply x. So we'll write this as p square minus 1 and then this is x plus greatest greater function of x. Now first interval that we'll take is when x lies between minus 2 and minus 1. In this case, greatest greater function of x is simply minus 2. So we'll write this as x minus 2 and then minus 2. Now when x is minus 1, this value is going to be, now this is 0 and this is minus 2. So it will be this minus 2 p square minus 1 minus 2. And here in this interval, it is simply going to be q into e to the power x plus e to the power minus x by 2 plus mod of p into x minus 1. Now the question says it is continuous in minus 2 to plus 2. So we'll start writing left hand limit, right hand limit and function value at minus 1. Now f minus 1 negative, it will be, now this is minus 3 p square minus 1 minus 2. F minus 1, it is minus 2 p square minus 1 minus 2. And f minus 1 positive, it will be q e to the power minus 1 plus e by 2 and minus 2 mod p. Now first we equate these two. Now if we equate these two, we get p square minus 1 equals 0. That is value of p is plus or minus 1. And if we put p as plus or minus 1 and we equate this, we get minus 2 and it will be equal to q and this is 1 upon e plus e by 2 and then minus and mod p is 1. So it will be this minus 2. So here value of q is 0. So for this function, p is plus minus 1 and q is 0. So if it is plus minus 1, this term will be gone. Here it will be this gone and here we won't have this and this is 1. So this function will be minus 2 when x lies between minus 2 and minus 1 and it will be x minus 1 when x lies between 1 and 2. So we'll write this fx as minus 2 when x lies between minus 2 and minus 1 and it will be x minus 1 when x lies between minus 1 and 2. Now we need to find the value of f of minus 1 by 2. Now f of minus 1 by 2 is minus 2. So we'll have f of minus 2 and at minus 2 this value is not defined. So this f of minus 2 is not defined for this question. And therefore answer to this question is this option D. Now here the question is which of the following statements is or are correct. Now this first one is fx is greatest integral function of log x plus under root of fraction part of log x. Now if we take log x as t, then we can write f e to the power t as greatest integral function of t and under root of fraction part of t. Now this we have already worked out. In one of the previous questions, this function is continuous for all x belongs to R, so it is continuous for all t belongs to R. That is, this function is continuous for all x greater than 1. That means this statement 1 is correct. Now the statement 2 is this limit exists and is equal to L, then we need to find the value of a plus 1 by L. Now this part B is limit x tends to minus 2, and this is 3x square plus a x plus 1 upon, and we can factorize this as x plus 2 into x minus 1. Now this is 0, and the numerator if we put x as minus 2, it will be this 12 plus 1 13, and then minus a. Now this limit exists and is equal to L if it is an indeterminate form. That means it has to be 0 upon 0 form. So from here we can say value of a, it should be 13. Now if we put a as 13, we can write this limit as limit x tends to minus 2. Now this is 3x square plus 13 x plus 1 plus 1, and the denominator, let this as x square plus x minus 2. Now this is 0 upon 0 form. We can use L'Hopital's rule. So it will be this limit x tends to minus 2, and this is 6x plus 13 upon 2x plus 1. Now this is 13 minus 12, 1 upon, and this is minus 3. So value of L is minus 1 by 3. Now we need to find the value of a plus 1 by L. Now a is 13 and 1 by L is minus 3. So this value is 10. That means this option B is correct. Now this third one, it says this function is defined from minus 1 to 1 to minus 1 to 1, and it is defined as fx equals x square into signum x. Now we can write this as minus x square if x is less than 0 and plus x square if x is greater than or equal to 0. Now if we draw this graph, it will be this minus x square and plus x square. Now this function, it is both 1 1 and on 2. That means this option C is also correct. And finally, for this option D, it says f is continuous on minus 1 to 1 and f minus 1 equals 4 and f1 equals 3. Now this pi, it lies between 3 and 4. Therefore, from intermediate value theorem, we can say there exists an R in the interval minus 1 to 1 such that fr must be equal to pi. That means the statement D is correct. So for this question, all the 4 statements, they are correct. Now here the question is, if f is a differentiable function, so it's fine. fxy equals fx plus fy plus x plus y minus 1 upon xy for all xy greater than 0, and f dash 1 is to find the value of greater function of f e to the power 100. Now what we'll do is we'll find the value of f1. We'll put x and y as both 1. So it'll be this f1 and it'll be this 2f1, and here it will be this 1. So from here we can say value of f1 it will be minus 1. Now we'll write f dash x. Now we'll write f dash x as this limit h tends to 0 f x plus h minus fx upon h, and we'll write this as limit h tends to 0, and this is fx into 1 plus h upon x minus fx whole divided by h. Now we'll use this formula fxy is fx plus fy plus x plus y minus 1 upon xy. So we'll write this as limit h tends to 0. Now this is fx plus f1 plus h upon x, and then plus x plus 1 plus h upon x minus 1 upon x plus h minus fx whole divided by h. Now this fx and fx will cancel, and this 1 and 1 will also cancel. Now what we'll do is we'll add 1 and subtract 1. So we can write this as limit h tends to 0, and this is f1 plus h by x, and we can write this plus 1 as minus of minus 1, and we know that minus 1 is f1. So this first part will be f1 plus h upon x minus f1 upon h, and then plus this limit h tends to 0, and if we simplify this, we'll get this as h upon x minus h whole divided by h, and here this is x plus h. Now here if we multiply and divide it with x, now this is derivative of this function at 1, so it will be this f dash 1 by x, and this is your f dash x plus, now here we can cancel h with h, so it will be 1 upon x minus 1, and here we have this 1 upon x, so it will be this 1 upon x into x minus 1. Now we are given that f dash 1 is 2, so if we put f dash 1 as 2, so it will be 2 upon x plus 1 upon x square minus 1 upon x, or we can write f dash x is 1 upon x plus 1 upon x square. Now we integrate this function, we can write fx equals log x minus 1 upon x plus c. Now f1 is minus 1, so if we put x as minus 1, this is minus 1, 0, minus 1 plus c, that means value of c is 0. So in this case our function fx is log x minus 1 by x. Now we need to find the value of greatest integer function of f e to the power 100. Now first we'll find f e to the power 100. Now this f e to the power 100, it will be this 100 minus e to the power minus 100, which is 100 minus some small value, and if we take greatest integer function of f e to the power 100, it will be 100 minus h, which is 99. So answer to this question is 99. And this question we are given this function fx, which we can write as fx equals, now this is under root of, and we'll take these terms together and these two terms together, so it will be this x minus n and then minus x minus n whole square if x lies between n and n plus 1 by 2, and it will be 1 minus x minus n when x lies between n plus 1 by 2 and n plus 1. Now we'll check its continuity at n plus 1 by 2. Now f n plus 1 by 2 negative, it will be x minus n will be 1 by 2. So it will be this under root of 1 by 2 minus 1 by 4. So it will be this 1 by 2 and f n plus 1 by 2. It will be 1 minus 1 by 2, which is 1 by 2. So this function, it is continuous at n plus 1 by 2. Now we'll check continuity at n. Now if it is n, here also it should be n. So what we'll do is, here we'll replace n with n minus 1. And if we replace n with n minus 1, it will be 1 minus x minus n plus 1 when x lies between n plus 1 by 2 and n. And in this case, it will be simply n minus x. Now if we look at f n negative will be n minus n 0, and f n positive, it will be, we'll put x as n, it will be 0. So this function is continuous for all x in this interval minus 5 to plus 5. Now we have to check its differentiability. Now if we differentiate this, we can write f dash x as one upon 2 under root of x minus n whole square, and it will be equal to 1 minus 2 into x minus n when x lies between n and n plus 1 by 2, and it will be minus 1 in both the cases, n plus 1 by 2 x and n plus 1, and also n minus 1 by 2 x and n. Now if we put x as n, this approaches infinite. So that means this fx is not differentiable at all the integral values at x equals n. Now what about n plus 1 by 2? Now if we put x as n plus 1 by 2, its right hand derivative is simple. It is minus 1. We have to find its left hand derivative. Its left hand derivative will be f dash n plus 1 by 2 negative. Now this is 1 minus 2, and x minus n is this 1 by 2 upon 2 into 1 by 2 minus 1 by 4, and this value is 0. So this function is not differentiable at x equals n plus 1 by 2. So in between minus 5 to plus 5, this function is not differentiable at plus minus 4, plus minus 3, plus minus 2, plus minus 1 and 0. And it is also not differentiable at plus minus 0.5, plus minus 1.5, plus minus 2.5, plus minus 3.5, and plus minus 4.5. So here we have 10 values, 10 and 18 plus 1, 19. So number of values of x where this function is not differentiable is 19, and that is the answer to this question. Now here the question is, for a differentiable function fx where f dash x is greater than 0, we are given that this limit x tends to 1 e to the power 2fx minus 2 e to the power fx plus 1 plus e square cos x minus 1 upon, now secant square theta minus 1 is tan square theta, so it will be this tan square x minus 1, and this is equal to 7 e square upon 2. Now what we'll do is, we'll add e square and subtract e square, so we can write this as this limit x tends to 1, and here it will be e to the power fx minus e whole square and minus, and this is e square 1 minus cos x minus 1 whole divided by tan square x minus 1, and it is equal to 7 e square by 2. Now we can write this as limit x tends to 1, and this is e to the power fx minus e upon 10x minus 1 whole square and then minus e square, and this is 1 minus cos x minus 1, and we multiply and divide everything with x minus 1 square. So it will be this 10 square x minus 1 upon x minus 1 square, and this is 7 e square by 2. Now x square, it is continuous, we can take this limit inside, so it will be this limit x tends to 1 e to the power fx minus e upon 10x minus 1, and then minus e square, and this is tan limit 1 by 2, and this is 1. So it will be this e square by 2, and this is 7 e square by 2. Now this is e to the power f1 minus e upon 0. So it will be e to the power f1 minus e upon 0, and this limit will have a finite answer if this is an indeterminate form. That means value of f1 must be 1. So when x is 1, y is 1. So we have got one result. Now if it is 0 upon 0 form, we can apply L'Hopital's rule. Then we can find, and this square. Then we can write limit x tends to 1. Now this is e to the power fx into f dash x upon secant square x minus 1 whole square, and this is equal to 7 plus 1, 8 e square upon 2. So it will be this 4 e square. Now we'll put x as 1. So it will be this e square and then f dash 1 square upon 1, and this is 4 e square. So from here we can say value of f dash 1 is 2. Since in that question it is given that f dash x is greater than 0. So we have f1 and f dash 1. Now we'll write equation of tangent to this curve at 1 comma f1, and f1 is also 1. So it will be y minus 1 and then f dash 1. F dash 1 is 2 into x minus 1. So this equation will be 2x plus y equals 1. Intercepts are 1 by 2 and 1. So area of triangle formed by coordinate axis will be 1 by 2 into 1 by 2 into 1, and which is 1 by 4. Now we need to find the value of 1 upon delta. Now 1 upon delta is nothing but 4, and that is the answer to this question. So this is 4. Now here the question is, we are given this function fx which is 23 minus 2 to the power. Now here it is minus x square plus 2x plus 3, and gx is greatest linear function of fx by mu. Now it says find the sum of all values of mu for which gx is discontinuous for at least one real value of x, and this mu is a natural number. What we'll do is first we'll find range of fx. Now if we look at this, minus x square plus 2x plus 3. So what we'll do is we'll minus 1 and add 1. So we can write this as 4 minus x minus 1 whole square. Now 4 minus x minus 1 whole square, it is always greater than minus infinite and will always be less than or equal to 4. Now if we take power of 2, then it will be 2 to the power minus infinite, and this is 2 to the power 4 minus x minus 1 square, it will be less than 2 to the power 4. Now this is 0. 2 to the power 4 minus x minus 1 whole square, that is less than 16. Now if we take a minus sign, then sign will change. So we can write this as minus 16, it is less than minus 2 to the power 4 minus x minus 1 whole square, and will be less than 0, and then we'll add 23. Now 23 minus 16 is 7. So range of this function is from 7 to 23. So value of this function fx, it will lie between 7 and 23. Fx upon mu its greatest linear function, it will be continuous if mu is greater than or equal to 23. So for all those values, this greater function will be 0. In that case, this function will always be a continuous function. So it is discontinuous at one value if mu is less than or equal to 22. That will give us 22 different values of mu. For this question, we need to find sum of all the values of mu. Now, sum of all the values of mu is simply sum of first 22 natural numbers. So this is n plus 1 divided by 2. So this is 23 into 11. So this is 23 and 23, which is 253. So answer to this question is 253. Now, in the questions, we are given this function fx, which is x square minus 3x plus 2. So it will be this x minus 1, x minus 2, and then mod of this cubic function. And if we factorize this, it will be this x minus 1, x minus 2, x minus 3, and plus mod of sine x plus pi by 4. Now we need to find number of points at which this function fx is not differentiable 0 to 2 pi. Now if we look at this mod function, it is not differentiable at 1, 2 and 3. But then we have this x minus 1 and x minus 2 in the product. So at x equal to 1, this x minus 1 will be 0. So in that case, it will be differentiable. At 2 also, we have this x minus 2 will be differentiable. So the only point where this product is not differentiable is x equals 3. So from here, we'll get this value as x equals 3. And here sine x plus pi by 4 is not differentiable at all the points where sine x plus pi by 4 is 0. And x plus pi by 4 is 0 at n pi. So here the value of x should be n pi minus pi by 4. Now if we put n as 1, we'll get x as 3 pi by 4. And if we put n as 2, we'll get x as 7 pi by 4. So the number of points where this function is not differentiable is 3, and that's your option C. Now here the question is, if f is a differentiable function, so it's fine. F dash x equals f dash minus x for all x belongs to R, then which of the following is correct? Now if we integrate this, we can write fx and it will be equal to minus f minus x plus c, or we can write fx plus f minus x will be constant. That is, if f1 equals f2, then we need to identify whether f minus 1 equals f minus 2. Now if we put x as 1, we can write f1 plus f minus 1, it is c, and it will also be equal to f2 plus f minus 2. Now if f1 equals f2, then clearly from here we can say f minus 1 must also be equal to f minus 2. That means this statement A is correct. Now in this, if we put x as 0, we can write c as 2 times f0. So from here we can say fx plus f minus x, it should be equal to 2 times f0. That means this option D is also correct. Now if you look at this option B, then we are given 1 by 2 fx plus 1 by 2 fy, it is equal to f 1 by 2 x plus y. Now if we look at this option C, it says let fx be an even function. If it is even, then f minus x is equal to fx. So in that case, it will be 2 times fx and it will be equal to 2 times f0. So from here, we'll get this condition that fx equals f0, and this f0, it may be 0 and it may not be 0. So this C is not necessarily true. Now in B, if we replace y with minus x, we can write fx plus f minus x will be 2 times f0, which matches with our condition. But then in one special case, this condition is equal to this condition. But generally for different values of x and y, this condition is not true for our function. So this option B may not be correct. So the correct options are only A and D. Right, the question is, gx is a polynomial satisfying gx into gy, it is equal to gx plus gy plus gxy minus 2. Now what we'll do is, we'll find the value of G1. Now we'll put x and y as both 1. We can write G1 square will be equal to 2 times G1 plus G1 minus 2. So it will be this G1 square minus 3G1 plus 2 equals 0. That means value of G1 is either 1 or value of G1 is 2. Now if we put y as 1 in this, taking G1 as 1, we'll get Gx and will be equal to Gx plus 1 plus Gx minus 2. From here we'll get this condition that Gx is a constant function, but it says G2 is equal to 5. That means G1 is not equal to 1. So G1 has to be 2. Now what we'll do is we'll replace y with 1 by x. Now if we replace y with 1 by x, we can write Gx into G1 by x, it is equal to Gx plus G1 by x plus G1 minus 2. Now G1 is equal to 2, so it will cancel. So from here we get this condition that Gx plus G1 by x minus Gx G1 by x, it is equal to 0. Now we'll subtract 1 both sides. Now we'll take this together and this together. So we can write Gx minus 1, and here we'll take minus G1 by x common, and then it will be Gx minus 1. This is equal to minus 1. We'll factorize and multiply this minus 1 here. We can write Gx minus 1 into G1 by x minus 1, it is equal to 1. Now it is given that Gx is a polynomial and Gx minus 1, they should cancel x for all the values of x. So that means this Gx minus 1, it should be of the form plus or minus x to the power n. So from here we get Gn as plus or minus x to the power n plus 1. Now here we must decide if it is plus sign or minus sign, because it cannot be both. Then in that case this Gx, it won't be a function. Now it is given that G2 is 5. Now we write x as 2, so it will be plus minus 2 to the power n plus 1. So from here we can say it is a plus sign and value of n is 2. So this function Gx, it will be simply x square plus 1. Now here we need to find the value of this limit x tends to 3 Gx. Limit x tends to 3 and Gx is x square plus 1. So this is 9 plus 1, 10. And that's your option C. Now we are given this function fx and we need to find the value of f0 if f is continuous at x equals to 0. Now we'll multiply this x inside. We can write fx as 1 upon 1 plus x, and this is x upon 1 plus x into 1 plus 2x, and this is x upon 1 plus 2x into 1 plus 3x. It goes all the way up to infinite. Now this is 1 upon 1 plus x, and we'll split this using partial fractions. So it will be 1 upon 1 plus x minus 1 upon 1 plus 2x. In the same way we can write this as 1 upon 1 plus 2x minus 1 upon 1 plus 3x up to infinite. Now all these terms, they'll cancel. We'll get this fx as 2 upon 1 plus x when x is unequal to 0 and when x is unequal to minus 1 by n. Now it says this function is continuous at x equal to 0. In that case, this limit x tends to 0 fx, it will be simply 2 and it must be equal to function value. So in this case, value at 0 must be 2. Now the question is, we are given this function fx, which is this summation r very small 1 to n x to the power r plus x to the power minus r whole square, where x is unequal to plus or minus 1. Now we'll simplify fx. Now this is r very small 1 to n. Now this is x to the power 2r plus x to the power minus 2r plus 2. Now this is geometric progression. It starts with x square. So this is a 1 minus r here is x square. So it will be x to the power 2n upon 1 minus x square and plus, now here in this case, first term is 1 upon x square and here will be 1 upon x to the power 2n minus 1 upon 1 upon x square minus 1 and this is plus 2n. Now we'll take this 2n on the left hand side, then we can write fx minus 2n will be this x square into 1 minus x to the power 2n upon 1 minus x square and then plus, here it will be 1 minus x to the power 2n upon 1 minus x square and then x to the power 2n. Now we can write this as x to the power 2n plus 2 plus 1 into 1 minus x to the power 2n upon, and here it will be 1 minus x square into x to the power 2n. Now it says we have defined this function gx and this gx is limit n tends to infinite fx minus 2n into x to the power minus 2n minus 2 into 1 minus x square if x is unequal to plus or minus 1 and it is minus 1 for x equals plus or minus 1. Now first we'll simplify this. Now it will be this limit n tends to infinite. Now fx minus 2n is x to the power 2n plus 2 plus 1 into 1 minus x to the power 2n upon 1 minus x square into x to the power 2n, that is multiplied with x to the power minus 2n minus 2 into 1 minus x square. Now this 1 minus x square will cancel. When we multiply this here, we write this as limit n tends to infinite and this is 1 minus, this is 1 plus x to the power minus 2n plus 2 and here it is x to the power minus 2n minus 1. Now we have to show that this gx is continuous for all x in its domain. This region, when mod of x is less than 1, then in that case x to the power minus infinite, it will be infinite. In that case this gx, it is not defined. So gx is not defined when mod x is less than 1. Now when mod x is greater than 1, in that case x tends to minus infinite will be 0. Then this gx, it will be simply 1 into minus 1 and that is minus 1. And it is given that g plus or minus 1 is minus 1. So basically this gx, it is a constant function in its domain and therefore it is continuous in its domain. Now the question is, if fx plus y is equal to fx into fy for all x and fx is 1 plus gx into capital Gx, where this limit x tends to 0, gx is equal to 0 and this limit x tends to 0, gx, it exists, then prove that f is continuous at all x belongs to R. Now if we put x and y is both 0, we can write f0 is equal to f0 square. So from here either f0 is 0 or f0 is 1. Now if we put y as 0, fx into f0 is 0, which is a constant function. So for this, fx will be a constant function which is continuous for all x belongs to R. Now what if f0 is 1? So we'll take this case when the value of f0 is 1. Now we'll check for continuity of fx at x equals 0. Now f0 negative, it will be 1 plus g0 negative into g0 negative. Now g0, it is 0. That means this f0 negative is 1. And f0 positive is 1 plus g0 positive and g0 positive. Now this again is 1. So that means this function fx is continuous at x equals 0. Now if fx is 0, then this limit, it cannot be 0. So we have to discard this possibility f0 equals 0. So the only condition that remains here is value of f0 must be 1. Now once we know that f is continuous at 0, that is fh equals f minus h, and it is equal to f0, which is 1. We have to prove that it is continuous for all x belongs to R. Now we'll check for its continuity at any point x equals a. Now f a positive is f a plus h. Now it will be this f a into fh, and fh is simply 1. So it will be equal to fa. And the same way f a negative is f a minus h, which is f a into f minus h, and f minus h is again 1. So it is equal to fa. So for any point a, fa positive is equal to fa negative is equal to fa. That means this function f is continuous at all the points. Now here the question is, we are given this function fx, which is cosec 2x cosec 2 square x up to cosec 2 to the power nx, and gx is fx plus cot 2 to the power nx. Now here what we'll do is we'll add cot to the power 2nx and subtract cot to the power 2nx. Now first we'll simplify this. Cosec 2 to the power nx plus cot 2 to the power nx. Now we can add this as sine and cos. So it will be 1 plus cos 2 to the power nx upon sine 2 to the power nx. Now if we apply half angle formula, so it will be this 2 cos square 2 to the power n minus 1x minus 1 upon this is 2 sine 2 to the power n minus 1x into cos 2 to the power of n minus 1x. Now this 1 and 1 will cancel, this 2 will cancel, this cos will cancel once, so it will be equal to cot 2 to the power of n minus 1x. So now we have this as plus cot 2 to the power of n minus 1x, and the term previous to it, it is cosec 2 to the power of n minus 1x. Now again it will be this cosec 2 to the power n minus 1x into cot 2 to the power n minus 1x. Now here it will be cot 2 to the power of n minus 2x, and this series will keep generating itself till in the end we have cosec 2x plus cot 2x, and if we simplify this, then we'll simply get cot x. So that means our function fx, it is nothing but it is cot x minus cot 2 to the power of nx. Now if we take cot nx here, we can write fx plus cot 2 to the power nx is nothing but this is cot x. So basically our function gx is cot x when x belongs to 0 to pi by 2. Now we are given this function hx, and it says find the value of p to make the function h continuous at x equals 0. Now first we'll find its right hand limit. So it will be this h 0 positive, and it will be this limit x tends to 0 positive, and this is cos x to the power gx, and gx is cot x plus secant x to the power cosec x. Now cos 0 is 1 and cot 0 is infinite and secant 0 is 1 and cosec 0 is infinite. So both of them, they are 0 to infinite forms. So what we'll do is we'll use the shortcut directly. So now we can write this as this e to the power limit x tends to 0 positive, and this is cot x log cos x, and plus will be e to the power this limit x tends to 0 cosec x into log secant x. Now we can write this as e to the power limit x tends to 0 log cos x upon tan x, and plus this is e to the power limit x tends to 0 log secant x into sin x. Now both of them, they are 0 upon 0 forms. So we can use L'Hopital's rule. So it will be this e to the power and then this limit x tends to 0. Now this is log x is 1 upon cos x and cos x is minus sin x. So it will be this, and derivative of tan x is secant square x. And plus e to the power this limit x tends to 0. Now this is 1 upon secant x into tan x will be this tan x, and then derivative of sin x is cos x. Now this is tan 0 0 secant 0 1. So this is e to the power 0 1, and here also it is e to the power 0 1. So its right hand limit is 2. Now we'll find its left hand limit. Now h0 negative is this limit x tends to 0 negative e to the power x plus e to the power minus x minus 2 cos x upon x sin x. What we'll do is we'll use series expansion here. So this is limit x tends to 0 negative. This is 1 plus x square upon 2. This is 1 minus x plus x square upon 2, and then minus 2, and this is 1 minus x square upon 2 whole divided by x, and this is x minus x cube upon factorial 3. Now here this 2, it will cancel. So here minimum power of x in the numerator is x square and the denominator is also x square. So answer to this limit is coefficient of x square. Now this is x square by 2, 1, and 1 plus 1, it is 2. So answer to this limit is 2. Now left hand limit is 2, right hand limit is 2. So this function will be continuous if the value of p is 2. Now the question is, we are given this function fx, which is defined as greatest integral function of tan x plus under root of fraction part of tan x when x belongs to 0 to pi by 2. Now what we'll do is we'll take tan x as t. So we can write this function as y, and this is greatest integral function of t and under root of fraction part of t when t is greater than or equal to 0. Now this we have already studied. So by using graph or analytically also, this function, it is always continuous but not differentiable at integral points. So this is continuous for all t greater than or equal to 0. That means this function is continuous in 0 to pi by 2. Actually we have solved this question thrice. First one was greatest integral function of x plus under root of fraction part of x. Second one was greater function of log x plus under root of fraction part of log x, and this third one is greater function of tan x plus under root of fraction part of tan x. All the three questions, they are essentially the same. Here the question is, we are given this function fx and we need to check its differentiability in -2 to 2. Now we write this fx first when x lies between -2 and -1. Now between -2 and -1, mod x is minus x, and this fractional part of x is x plus 2. So it will be this cos pi by 2 minus x plus, and then minus this x plus 2. Now between minus 1 and 0, it will be this cos pi by 2, and here it is minus x, and here it will be this x plus 1. Between 0 and 1, it will be cos pi by 2, and now this is x and this is also x, and when x lies between 1 and 2, it will be under root of 4x square minus and plus 9, and I think this is fraction part of x in product with this expression, so it will be this x minus 1, and at x equal to 2 it will be 0. Now this 4x square minus 12x plus 9 is actually mod of 2x minus 3. So now we can write this function fx as, now this first one is cos, and this is minus 2x minus 2. So it will be cos x plus 1 pi when x lies between minus 2 and minus 1. Now here it will be cos 2x plus 1 into pi by 2 when x lies between minus 1 and 0. Now this is cos 0, and cos 0 is 1 when x lies between 0 and 1. Now this is mod 2x minus 3, so it will be minus 2x minus 3 when x is greater than 1 but less than 3 by 2 into x minus 1, and it will be 2x minus 3 into x minus 1 when x lies between 3 by 2 and 2, and at 2 this value is 0. So that is the definition of this function fx. Now first we'll check its continuity. Now at minus 1, f minus 1 negative will be this cos 0, and cos 0 is 1, and at minus 1, which is same as its right hand limit, it will be cos pi by 2, and cos pi by 2 is 0. So it is discontinuous at x equals minus 1. Now in the same way we write f0 negative. f0 negative is cos pi by 2 0, and f0 and f0 positive, it is 1. So again they are not equal, so it is discontinuous at x equals 0. So this function is not differentiable at x equals to 0, plus minus 1, 3 by 2 and 2. Now here the question is, we are given these 4 functions and then we have to match them with the options given in column 2. Now we'll start with this first function, which is f1x. Now f1x is defined as greatest linear function of 4x upon pi into signum of x square minus x plus 1. Now if we look at this quadratic, x square minus x plus 1, d here is minus 3, which is less than 0, and coefficient of x square is positive. That means this is greater than 0 for all x belongs to R. And if fx is positive, then signum of fx is always 1. So this value, it is plus 1. So our function f1x is nothing but it is this greatest linear function of 4x upon pi. Now it is given that x lies between minus 2 and plus 2. Now we look at 4x upon pi, it will be minus 8 upon pi less than equal to 4x upon pi and be less than equal to 8 upon pi. Now 8 upon pi is nearly 2.55, so it will be minus 2.55 less than equal to 4x upon pi and will be less than equal to 2.55. Now this function, it will be discontinuous and non-differentiable at x equals 0, plus minus 1 and at plus minus 2. And range of this function, it will be this minus 3 plus minus 2, plus minus 1 and 0. Now we look for the second one. Now this second function we have is f2x equals cos inverse of signum cos 2x minus 1 by 2 into pi. Now we can write this as cos inverse and then signum of, now we write this as cos pi by 2 minus pi x, which is sine pi x. So this is cos inverse signum of sine pi x. Now we'll start drawing the graph of f2x from minus 2 to plus 2. Now this is minus 2, minus 1, 0, plus 1 and plus 2. Now whenever x is an integer, this is sine n pi is 0, signum 0 is 0 and cos inverse 0 is pi by 2. At all these integer points, value is pi by 2. Now when x lies between 0 and 1 and minus 2 and minus 1, sine pi x is positive. In that case, signum function, it is 1 and cos inverse 1 is 0. So in between these two, value is 0. And when x lies between minus 1 and 0 and 1 and 2, sine pi x is negative. And signum of negative function is minus 1. Cos inverse minus 1 is pi. So in that case, we'll have this function, it will be pi. So that is the graph of f2x. Now if we look at points where it is discontinuous, 1, 2, 3, 4, 5, we have 5 points where this function is discontinuous. And at those 5 points, this function is also not differentiable. And its range is 0, pi by 2 and pi. Now f3x is maximum of fractional part of x plus 1 and fraction part of 5 minus x. Now integer doesn't affect fraction part function. So it will be this maximum of fraction part x and fraction part of minus x. Now we'll draw this graph. Now both these functions, they are periodic with period 1. So we'll draw the graph in 0 to 1. Now that's the graph of fraction part of x. And this is the graph for fraction part of minus x. Now we have to choose maximum of the two. Now here it will be this value, and here we have values at 0 and 1. So at 2 also will be same. Now this is minus 1 and minus 2 will be same here, and it will be same in this way. So that's the graph of this function. f4x is mod x plus greatest new function of x square. Now clearly it is discontinuous at 0, plus minus 1, plus minus 2, and f4x will be x when x lies between 0 and 1, when x lies between minus 1 and 0, and between 1 and 2, its greater function square will be 1. So then it will be mod x plus 1, and in between minus 2 and minus 1 will be simply mod x plus 4. Now if we draw this graph, between 0 and 1 this is x, between 1 and 2 it is x plus 1. So at 1 this value is 2, at 2 this value is 3. So it will be from 2 to 3. So this is 0, 1 and 2. Now between minus 1 and 0, this is minus x plus 1. Now at 0 this is 1, and at minus 1 this is 2. And here it will be this minus x plus 4. So when x is minus 2, this is 6. And when x is minus 1, this is 5. So it will be from 5 to 6. So that is the graph of this function. Now the question is, the differentiable function satisfies this relation, which is fx plus y, that is equal to fx plus fy plus 2xy minus 1 for all xy belongs to R, and says if f dash 0 is under root of 3 plus a minus a square, find fx and prove that fx is greater than 0 for all x belongs to R. Now we'll find the value of f0, and for that we'll put x and y as both 0. So this is f0, and here will be 2 times f0 minus 1. So from here we can say value of f0, it must be 1. Now we can write f dash x as limit h tends to 0. Now it will be this fx plus h minus fx upon h. Now fx plus h is fx plus fh plus 2xy minus 1. So it will be this limit h tends to 0, and then it will be this fx plus fh plus 2xh minus 1 and minus fx whole divided by h. Now this fx and fx will cancel. Now we can rewrite this as limit h tends to 0, and here it will be fh minus 1, and we can write this one as f0 upon h and plus 2x. Now this is nothing but this is f dash 0. So we can write this f dash x as f dash 0 plus 2x. Now we integrate this, we can write fx equals, now this 2x is simply x square, and here will be this f dash 0x and plus c. Now when x is 0, f0 is 1. So this is 1 and it is equal to c. So value of c is 1. So we can write this function fx as x square plus, and then f dash 0 is defined as 3 plus a minus a square x and plus 1. Now we need to show that this function is positive for all x belongs to R. Now basically it's a quadratic equation. Now if we write its discriminant will be b square, which is 3 plus a minus a square and then minus 4ab. So there will be minus 4. Now we can write this as minus a square plus a minus 4, and this is always negative. And when d is less than 0 and coefficient of x square is positive, that means this fx is greater than 0 for all x belongs to R. And this is what we need to prove in this question. Now the question is, we are given that fxy, it is equal to xfy plus yfx for xy belongs to R positive, and says it is differentiable on 0 to infinite. Now what we'll do is we'll find the value of f1. Now we'll put x and y as both 1. So it'll be this f1 and it'll be equal to f1 plus f1. So clearly value of f1 is 0. Now we'll find f dash x. Now this f dash x will be this limit h tends to 0 fx plus h minus fx upon h, which is this limit h tends to 0, and this is f, and x into 1 plus h upon x minus fx upon h. Now this is f x into y. Now we can write f x into y as x fy plus y fx. So it will be this limit h tends to 0, will be this x f 1 plus h upon x and plus 1 plus h upon x into fx minus fx whole divided by h. Now we'll split it in two parts. Now we can write this f dash x as, now we'll take x common from this, and it will be this limit h tends to 0 f1 plus h upon x divided by h, and we can write this as f1 because f1 is 0. And here if we cancel this fx, h and h will cancel, it will be simply f x by x. Now if we multiply and divide by x, now this x will cancel, this is f dash 1. So we can write this f dash x as f dash 1 plus f x upon x. Now we can write this as dy by dx, and we'll take it on the left hand side. So this is minus y by x, and this is f dash 1, which is linear differential equation in y. Now first we'll calculate its integrating factor. Its integrating factor will be e to the power minus integral of 1 by x dx, which is e to the power minus log x, which is simply 1 by x. So we'll get this as y, which is fx into 1 by x, and then into this integral f dash 1 by x into dx. Now this is fx upon x, and it is f dash 1 ln x plus c, or we can write fx equals f dash 1 into x log x plus cx. Now we know that f1 is 0. So if we put x as 1, we'll get c as 0. So our function fx will be simply f dash 1 into x log x, and that is the answer to this question. Now here we are given that e to the power minus xy into fxy, it is e to the power minus x fx plus e to the power minus y fy for all xy belongs to R positive, and f dash 1 it is equal to e. Now we'll find the value of f1 also. Now if we put x and y as 1, we can write e to the power minus 1 f1 equals e to the power minus 1 f1 plus e to the power minus 1 f1. Now from here we can say value of f1 is 0. So we have f1 and we also have f dash 1. Now what I'll also do is I'll write this fxy as e to the power xy into e to the power minus x fx plus e to the power minus y fy. Now we'll find f dash x. Now we'll write this f dash x as this limit h tends to 0 fx plus h minus fx upon h, and we are going to write this as limit h tends to 0, and we'll take this x common, it will be x into 1 plus h upon x minus fx by h. Now this is limit h tends to 0. Now this is fxy, and fxy is e to the power xy, which is e to the power x plus h, and then e to the power minus x fx plus e to the power minus 1 plus h upon x into f1 plus h upon x minus fx whole divided by h, and that's your f dash x. Now if we multiply it, then we'll write f dash x as this limit h tends to 0. Now it will be this e to the power h fx plus, and here it will be e to the power x plus h minus 1 minus h upon x, and this is f1 plus h upon x minus fx whole divided by h. Now we'll take fx together. We can rearrange this as this limit h tends to 0 fx into e to the power h minus 1 upon h, and then plus this limit h tends to 0, and here it is e to the power x plus h minus 1 minus h upon x f1 plus h upon x. Now we know that f1 is 0, so we can write this as f1 whole divided by h. Now we'll multiply and divide it with x also. Now this is f dash x and this is standard limit 1, so it will be this fx plus, now if we put h as 0, this is e to the power x minus 1 upon x into, and this is derivative of f at 1, and there will be f dash 1. Now we are given that f dash 1 is e. So if we put f dash 1 as e, we can write this as f dash x equals fx plus e to the power x upon x. Now if we multiply with e to the power minus x, we can write e to the power minus x f dash x minus e to the power minus x fx, it is equal to 1 upon x, and this is nothing but this is derivative of e to the power minus x into fx. So it will be d by dx of e to the power minus x into fx, it is equal to 1 by x. Now we integrate this, we can write e to the power minus x fx, and it will be equal to log x plus c. Now when x is 1, fx is 0. So clearly value of c is 0. So we can write our function fx as e to the power x into log x. And that is the answer to this question. Right, the question is, a function is defined on minus 1 to 1 to minus pi by 2 to plus pi by 2. It satisfies this equation, which is fx plus fy. It is fx into under root of 1 minus y square plus y into under root of 1 minus x square. Now first is show that fx is an odd function. So what I'll do is I'll replace y with minus x. So now I'll be this fx plus f minus x, and here it will be fx into under root of 1 minus x square and then minus x into under root of 1 minus x square, which is nothing but f0. Now we need to find the value of f0, and for that what we'll do is we'll put both x and y as 0. So then it will be 2 times f0, and here it will be this f0. So clearly value of f0 is 0, which is 0. So from here we can clearly say f of minus x is minus fx. Therefore this function is an odd function. Now second is, if f is differentiable on minus 1 to 1 and f dash 0 is 1, then show that f dash x is 1 upon under root 1 minus x square. Now what we'll do is, for the second part, we are given that f dash 0 is 1 and this function fx is differentiable. So we can write f dash x as this limit h tends to 0, and it will be f x plus h minus fx upon h. Now we have already proved that this f is an odd function. We can write minus fx as f minus x. So it will be this limit h tends to 0, and we can write this as f x plus h plus f minus x upon h. Now this is fx plus fy. So now we'll write this as this limit h tends to 0, and here it will be this f x plus h under root 1 minus x square, and then minus x into under root of 1 minus x plus h whole square whole divided by h. Now what we'll do is, we'll let x plus h under root of 1 minus x square minus x under root of 1 minus x plus h whole square as t. Now as h tends to 0, it will be x into under root 1 minus x square, and here it will be minus x into under root 1 minus x square. So as h tends to 0, t tends to 0. Now we can write this as this limit t tends to 0, and this is ft. Now we'll multiply and divide with t also. So it will be this t and then t upon h. Now ft upon t is basically f dash 0. So we can write this as f dash 0 into this limit t tends to 0 and then t by h. And the question says f dash 0 is 1. So we'll put this as 1 and we'll again put back this value of t. So we'll write this f dash x as limit h tends to 0, and here we'll take x together and h together. So it will be this x into under root of 1 minus x square minus under root of 1 minus x plus h whole square and plus h into under root of 1 minus x square whole divided by h. Now in this part h and h will cancel. So we let this f dash x as under root of 1 minus x square and then plus this limit h tends to 0, and this is x, and here we'll rationalize it, and if we rationalize it we get 1 minus x square and then minus 1 plus x plus h whole square upon h and then into under root of 1 minus x square plus under root of 1 minus x plus h whole square. Now this is f dash x, this is under root of 1 minus x square, and this is limit h tends to 0, and this is x. Now here 1 and 1 will cancel, x square will also cancel, so we'll get this as 2hx plus h square upon h into under root of 1 minus x square plus under root of 1 minus x plus h whole square. Now we'll cancel this h and we'll put this limit h tends to 0. So we'll get this f dash x as under root of 1 minus x square plus 2x square upon 2 times under root of 1 minus x square. Now this 2 and 2 will cancel. Now we take this LCM, it will be under root of 1 minus x square and 1. So we have proved that f dash x is 1 upon under root of 1 minus x square. And that's our second part. F dash x is 1 upon under root of 1 minus x square. Now from this we have to determine the value of fx. Now f dash x is 1 upon under root of 1 minus x square. Now we integrate this. Now this is fx, and here this is sine inverse x plus c. Now when x is 0, f0 is 0. That means c is 0. So basically this function fx is sine inverse of x. And that is the answer to this question. Now the question is, a twice differentiable function f, it satisfies this relation, which is f x square plus y square, and it is equal to f x square minus y square plus f 2xy. It is given that f0 is 0 and f double dash 0 is to find the value of fx. Now if we put x as 0, then we can write f y square, it is equal to f minus y square plus f0, and f0 is 0. So from here we can say fh, it is equal to f minus h. And since this function is differentiable, it will be equal to f0, which is 0. Now we'll find f dash x. Now what we'll do is, we'll take this equation, which is f x square plus y square, and it is equal to f x square minus y square plus f 2xy, and we'll subtract fx square and we'll divide everything with y square. Now we'll take this limit y tends to 0. Now this is limit y tends to 0, and this is also limit y tends to 0, and this is limit y tends to 0. Now this is derivative of this function at x square. So this is f dash x square. Now here, since this is minus y square, we'll take minus here, and we'll put minus here. So this is minus, and this also is derivative of x square. This is right hand derivative and this is left hand derivative, and plus this limit y tends to 0 f 2xy upon y square. Now if we put y as 0, f0 is 0 and y is 0, so this is 0 upon 0 form. So we can write 2f dash x square, it will be equal to this limit y tends to 0. Now this is f dash 2xy into 2x upon 2y. And we differentiate this with respect to y, we can say f dash y square into 2y, it is equal to f dash minus y square minus 2y. Now for y equal to 0, we'll always get f dash y square is equal to minus f dash minus y square. If we put y as 0, we get f dash 0 as 0. Now again this is 0 upon 0 form. Now we multiply it with x and divide it with x. This is second derivative of this function at 0. So it will be f double dash 0. So we can write 2 times f dash x square, it will be f double dash 0 into 2x square. Now this 2 and 2 will cancel, and f double dash 0, it is given as 2. So we can write f dash x square, it is equal to 2x square, or simply f dash x equals 2x. Now if we integrate this, we get fx as x square plus c. Now we know that when x is 0, f is 0, that means c is 0. So our function fx in this case is simply x square. And that is the answer to this question. Here the question is, we are given this function fx, which is a differentiable function satisfying this relationship, which is f square x plus f square y plus 2 xy minus 1, it is equal to f square x plus y for all x belongs to R. It is given that fx is always greater than 0 and value of f root 2, it is equal to 2. We need to determine this function fx. Now if we put both x and y as 0, we'll get 2 times f square 0, and this is minus 2, and it will be this f square 0. So from here we'll get the value of f0 as root 2. So value of f0 is root 2. And this equation, what we'll do is we'll replace y with h. So we can write f square x plus h will be equal to f square x plus f square h plus 2 xh minus 1. Now we'll take this x on the left hand side. We can write f square x plus h minus f square x, and will be equal to f square h plus 2 xh minus 2. Now we'll divide everything with h. Now this is limit h tends to 0 both sides. Now we'll split this as limit h tends to 0 f x plus h minus fx upon h into fx plus h plus fx, and here we'll write this as this limit h tends to 0. We'll take these two together, so it will be this f square h minus f square 0 upon h and plus this 2x. Now this is f dash x and this is simply 2fx. So it is 2fx into f dash x, and here it is fh minus f0 and fh plus f0. Now fh plus f0 is 2 times f0, and then fh minus f0 upon h is f dash 0 and plus 2x. Now this is some constant. We'll cancel this 2 with 2. So we can write fx into f dash x as x plus a. Now if we integrate this, we can write fx whole square upon 2. It will be x square upon 2 plus ax plus c. So basically this function fx, it will be under root of x square plus 2ax plus some constant c dash. Now we are given two conditions. One of them is f0 is root 2 and f2 is 2. Now if we put x as 0, we'll get this as root 2 and will be equal to c dash. So value of c dash is 2. And if we put x as root 2, we can write 2 equals under root of 2 plus 2ax plus 2. Now we square it, we get a equals 0. So a is 0 and c dash is 2. So basically our function fx will be under root of x square plus 2, and that is the answer to this question. Now the question is, we are given a function which is defined as fxy equals 2fx minus fx upon y. It is differentiable on r positive such that f1 is 0 and f dash 1 is 1. Now this first part is show that fy is equal to minus f1 upon y. So what we'll do is we'll simply put x as 1. So it will be this fy equals 2fy minus f1 upon y. Now f1 is 0. So from here we can say fy is equal to minus f1 upon y. That means this first we have proved. Now second is prove that fx plus fy equals fx upon y. Now we are given that fxy equals 2fx minus fx upon y. Now if we interchange xy, we can write fyx as 2fy minus f y by x. Now if we equate these two, then we can write 2fx minus fx upon y, it is equal to 2fy minus f y by x. Now minus f1 upon y is fy. So we can write this as this is plus f x upon y. Now if we rearrange this, we can write 2fx minus fy, it will be equal to 2fx upon y. This 2 and 2 will cancel. So here it should be this minus and not plus. So that's our second result. Now third one is hence determine fx. Now what we'll do is we'll write f dash x. Now f dash x is this limit h tends to 0 f x plus h minus fx upon h. So it will be this limit h tends to 0. Now fx minus fy is fx upon y. So it will be this f1 plus h upon x, and this is h. Now we'll multiply and divide it with x. Now we are given that f1 is 0. So we'll write minus f1. Now this is nothing but this is derivative of this function at 1. So it will be this f dash 1 upon x. Now f dash 1 is also 1. So this is 1 by x. So our function is defined such that f dash x is 1 by x. Now we integrate this, we can write fx equals log x plus c, and f1 is 0. So log 1 is 0 plus c. So from here we get c is 0. So in this case, this function fx is simply log x, and that is the answer to this question. Now the question is, a differentiable function f, it satisfies the relation fx plus y plus f xy minus 1, and it is equal to fx plus fy plus fx into y for all xy belongs to R, and it says f1 is 2, f dash 0 is 1, and f dash minus 1 is minus 1. Find fx. Now again for this, what we'll do is we'll write f dash x. So this f dash x will be limit h tends to 0 fx plus h minus fx upon h. Now we'll replace y with h, and we'll use fx plus h minus fx from this equation. So it will be this limit h tends to 0, and here it will be this fh plus fxh minus fxh minus 1 whole divided by h. Now here we need the value of f0. So what we'll do is we'll put x and y as both 0. Now if we put x and y as both 0, we can write f0 plus f minus 1 will be equal to 3 times f0, or f minus 1 is 2 times f0. Now what we'll do is we'll add f minus 1 and we'll subtract 2 f0. Now we can rearrange this as this limit h tends to 0. One of the f0 we'll take it with fh, so it will be this fh minus f0 upon h plus this limit h tends to 0. One of them we'll take it with xh, so it will be hx minus f0 upon h, and then finally we have this minus, and then this limit h tends to 0 f minus 1 plus xh minus f minus 1 upon h. Now this is f dash 0. Now here we'll multiply and divide everything with x. This again is f dash 0, so it will be this f dash 0 x, and minus here also we'll multiply and divide everything with x. Now this is derivative of this function at minus 1, so this is x into f dash minus 1. Now f dash 0 is 1 and f dash minus 1 is minus 1, so it will be this 1 plus x and plus x, so it will be simply 1 plus 2x. So in this case f dash x is 1 plus 2x. Now if we integrate, we can write fx as x plus x square plus c. Now we are given that f1 is 2. So this is 2 and this is 1 plus 1 plus c implies c equals to 0. That means our function fx is x plus x square, and that is the answer to this question. Now here the question is, find a function continuous and differentiable for all x and satisfying this functional relation f x plus y into f x minus y, and it is equal to f square x, and it is given that f0 is unequal to 0. Now in this, what we'll do is we'll put y as h, then we'll get this relation that fx plus h into fx minus h, it will be equal to f square x, and if we put x as 0 and y as x, then we can write f of x into f of minus x, it will be equal to f square 0. Now what we'll do is we'll write f dash x. Now this f dash x will be this limit h tends to 0 f x plus h minus fx upon h. Now what we'll do is we'll write this fx as f square 0 upon f minus x. So it will be this limit h tends to 0 fx plus h minus f square 0 upon f minus x divided by h. Now we can write this as limit h tends to 0 f x plus h into f minus x minus f square 0 upon f minus x into h. Now somehow we have to express it as x plus y and x minus y. So what we'll do is we'll write this as this limit h tends to 0 and this is f h by 2 plus x plus h by 2, and here it will be this f h by 2 minus x plus h by 2 minus f square 0 whole divided by f minus x into h. Now this is fx plus y into fx minus y, and we know that it is equal to f square x. So it will be this limit h tends to 0 f square h by 2 minus f square 0 upon f minus x into h. Now we'll use a plus b into a minus b, so we can write limit h tends to 0 and this is f h by 2 minus f 0 upon h, and we'll write this as f h by 2 plus f 0 upon f minus x. Now this is nothing but this is f dash 0 if we multiply and divide it with 2. So it is 1 by 2 f dash 0, and here it is 2 f 0 upon f minus x. Now this 2 and 2 will cancel. So now we have f dash x as f dash 0 into f 0 upon f minus x. Now we have already proved that fx into f minus x is f square 0. So we'll replace f minus x with f square 0 upon fx. So it will be this f dash x equals f dash 0 into fx upon f0. Now we can write this as f dash x upon fx, and this is equal to f dash 0 upon f0, and this is some constant, say a. Now if we integrate this, then we can write log fx equals ax plus c, or fx is e to the power ax into e to the power c. And e to the power c is some other constant, say capital A. So it is a into e to the power ax, and that is the answer to this question. Now here the questions, we are given this function f such that f x plus fy, it is equal to f of fx plus fy, and it says f of h is equal to h for h lying between 0 and epsilon, where epsilon is a small quantity. Now we take this limit h tends to 0, then clearly f0 is 0. Now if we put y as h, we can write f of x plus fh, it will be equal to f of fx plus fh. Now fh is simply h, so we can write fx plus h, it is equal to f of fx plus h. Now in this, if we put y as 0, we can write fx plus f0, which is 0, that is equal to f of fx plus f0, which again is 0. So we can write fx as f of fx. So this f of fx is actually fx. So we can write fx plus h minus fx, and we'll divide everything with h. Then this is equal to 1, and we'll take this limit, h tends to 0. Now this is nothing but this is f dash x. So we'll get f dash x equals 1. Now if we integrate this, we'll get fx equals x plus c. Now f0 is 0. That means value of fx is simply x. And that is the answer to this question. Now the question is, we are given this function f, which is thrice differentiable, and it says fx plus y equals f x minus y plus y into f dash x plus y plus f dash x minus y. And in this, we are given that f0 is 0, f dash 0 is 1, and f1 is 2. Now what we'll do is, for this question, we'll put y as x. If we put y as x, then we'll get f2x as f0, which is 0, plus x into, now this is f dash 2x plus f dash 0, and f dash 0 is 1. So it will be f2x equals x into f dash 2x plus 1. Now we'll differentiate this. We can write f dash 2x into 2, it will be equal to f dash 2x plus 1 and plus this x as it is, and then will be this f dash 2x into 2. Now this f dash 2x will cancel once. Now again we'll differentiate, so we'll get f double dash 2x into 2, and it will be equal to x into f triple dash 2x into 4 plus 2 into f double dash 2x. Now 2 into f double dash 2x will cancel. So from here we'll get f triple dash 2x equals 0, or simply f triple dash x equals to 0. Now if we integrate this, we'll get f double dash x equals a. Now if we integrate this, we'll get f dash x equals ax plus b. And if we integrate this, we'll get fx equals ax square by 2 plus bx plus c. Now f0 is 0, then clearly c is 0. Now f dash 0 is 1. Now if we put f dash 0, f dash 0 is 1. That means value of b is 1. So b is 1, c is 0, and f1 equals 2. Now f1, it will be a by 2 plus 1, and it is equal to 2. That means value of a is 2. So this fx is actually x square plus x. And that is the answer to this question. Now the question is, let fx be a positive differentiable function satisfying f x plus y by 2, that is equal to under root of fx into fy for all xy belongs to R, and f dash 0, it is equal to 2. Find fx. Now we'll write f dash x. Now f dash x is this limit h tends to 0, f x plus h minus fx upon h, and we'll write this as limit h tends to 0, and this is 2x plus 2h by 2 and minus f 2x plus 0 by 2 upon h. Now it will be this limit h tends to 0, and here it will be under root of f2x into f2h minus, and it will be under root of f2x into f0 whole divided by h. Now what we can do is we can take under root f2x common. Now here also if we put, now we take it common, then we can write this limit h tends to 0, and then it will be this under root f2x, and here it will be under root of f2h minus under root of f0 whole divided by h. Now this is under root of f2x, and we can write this as limit h tends to 0 f2h minus f0 upon h, and it will be under root of f2h plus under root of f0. Now we'll multiply and divide it with 2. Now we have replaced fx with under root f2x into root f0. So we can write root f2x as fx upon under root f0. So it will be 2 times fx upon under root f0, and here it will be this f dash 0, and here it will be 2 times under root of f0. Now this 2 and 2 will cancel. We'll get this as f dash 0 into fx upon f0. And the question it says f dash 0 is 2. So we'll put f dash 0 as 2. And this question they are also supposed to provide the value of f0. So I think they have taken value of f0 as 1. So we'll take value of f0 as 1, and we'll say it is given with the question, because there is no way we can find the value of f0 with the given condition. So now this f dash x, it will be 2 times fx. Now we can write f dash x upon fx, it is equal to 2. Now we integrate, we can write log fx equals 2x plus c, or fx equals e to the power c into e to the power 2x. Now when x is 0, f is 1. That means e to the power c is 1. So our function fx in this case, it will be e to the power 2x. So I think one condition that is needed with this question is value of f0 is 1. Now here the question is, discuss the continuity of this function, which is fx equals greatest linear function of x into cos 2x minus 1 into pi by 2. Now this cos, it is always continuous and differentiable, and this greatest linear function, it is discontinuous at all integers where n belongs to z. So this greater function of x will be discontinuous at all integers, but then at integer points, if you look at this cos, it will be this cos 2n minus 1 into pi by 2, and cos odd multiple of pi by 2, it will be 0. So that means this function is going to be continuous at x equal to n also. So this function is actually continuous for every real x, and that means this statement 1 is correct. Now here the question is, we are given this function fx, which is greatest linear function of x plus greatest linear function of x plus 1 by 3 and greatest linear function of x plus 2 by 3. Now we need to find number of points where this function is discontinuous for x belongs to 0 to 3. Now this x, it is discontinuous at all integral points, So here we have two integral points, 1 and 2. Now second one will be discontinuous when x is n plus 2 by 3. So it will be this 2 by 3. And then 1 plus 2 by 3 is 5 by 3. And 2 plus 2 by 3 is 7 by 3. And here it will be discontinuous at n plus 1 by 3. So it will be this x equals 1 by 3. 1 plus 1 by 3 is 4 by 3. And 2 plus 1 by 3 is 7 by 3. Then here it should be this 8 by 3. N plus 2 by 3. 2 plus 2 by 3 is 8 by 3. So total number of points where this function is discontinuous is 8. And that's your option 3. Now here the question is, let f and g be real valued functions defined on the interval -1 to 1 such that g double dash x is continuous, g0 is unequal to 0, g dash 0 is 0, g double dash 0 is unequal to 0, and fx is gx into sine x. Now we have to find validity of these two statements. Now this is f dash 0 equals g0. Now we are given fx equals gx into sine x. Now we let f dash x as gx into cos x plus g dash x into sine x. Now if we put x as 0, we'll get f dash 0 as g0, cos 0 is 1, and then g dash 0 and sine 0 is 0. Now in the question it says g0 is unequal to 0. So from here we can say this f dash 0, it is equal to g0. That means the statement 2 is correct. Now second one is, we'll check this limit. Now this limit is limit x tends to 0. Now we'll write this as gx and we'll change it in sine and cos. So it will be gx cos x minus g0 upon sine x. Now this is 0 upon 0 form. We'll use L'Hopital's rule. We can write limit x tends to 0 gx sine x plus g dash x cos x upon cos x. Now we put x as 0, it will be g0 into 0 plus g dash 0, cos 0 is 1, and here this value is 1. And the question it says g dash 0 is 0, so value of this limit is 0. Now if we find f double dash x, then f double dash x will be gx minus sin x plus g dash x into cos x plus g double dash x sin x plus g dash x into cos x. Now if we put x as 0, we get f double dash 0 as g0 and sin 0. Sin 0 is 0. Now g dash 0 is 0. Now sin 0 is 0. And here g dash 0 is 0. So f double dash is 0. So it will be equal to f double dash 0. That means this statement 1 is also correct. Now value of this limit is equal to 0, which is also the value of f double dash 0. But these two results, they are not correlated. So basically both the statements are correct, but statement 2 is not a correct explanation of statement 1. So the answer is this option B. Now the question is, fx is x square minus 4 into mod of x cube minus 6x square plus 11x minus 6 plus x upon 1 plus mod x. Now we need to find set of points at which this function is not differentiable. Now this is x plus 2 into x minus 2, and it is x minus 1, x minus 2, x minus 3 plus x upon 1 plus mod x. Now looking at this function, it is not differentiable at 1, 2 and 3. But we have this factor x minus 2 which is multiplied to it. That means when x is 2, it will be 0. So that means it is differentiable at x equal to 2. So this first function, it is not differentiable at x equals 1 and 3. Now if we look at the second function, which is say gx, x upon 1 plus mod x, its definition changes at x equal to 0. So we have to check for differentiability at x equals 0. Now clearly this is continuous because x is continuous, 1 plus mod x is continuous, and 1 plus mod x is unequal to 0. So we'll straight away check for its differentiability. Now g dash 0 negative will be this limit h tends to 0, and this is minus h upon 1 plus mod h minus 0 upon minus h. Now this is plus 1, and g dash 0 positive will be limit h tends to 0 h upon 1 plus mod h minus 0 upon h, which also is 1. So this function, it is differentiable in x belongs to R. So this function fx, it is not differentiable at only 2 points, x equals 1 and x equals 3, and that's your option D. Now the question is, if this function is continuous and differentiable in 4 to 6, then a cannot be. Now we have this function fx, which is defined as greatest linear function of x minus 2 cube upon a into sine x minus 2 plus a cos x minus 2. Now this greatest linear function, it is not differentiable at integral points. So first we'll find out range of x minus 2 cube. Now this x, it lies between 4 and 6. X minus 2 will lie between 2 and 4. And if we take this cube, it will be 8 x minus 2 cube, and it will be 64. Now this greatest linear function, x minus 2 cube upon a, it must lie between m and n plus 1. Only then this function will be a continuous function. Now if we take values less than 8, we'll have many integral points. If we take values between 8 and 64, this value will have some values less than 1 and some values greater than 1. Then also it will be discontinuous. So that means here this a, it must be greater than or equal to 64. Then a can be 65 and 66, options C and D. Now the question is, let a is number of points of continuity of fx, which is defined as x minus 1 when x is rational, and it is x square minus x minus 2 when x is irrational. Now we have already studied such functions, and we know that the only points where this function will be continuous is when x minus 1 is equal to x square minus x minus 2. Now we can write this as, so here we'll get 2 points. So in this case, value of a is simply 2. Now b is number of points of discontinuity of this function fx, which is signum of x cube minus 3x plus 1. Now if we look at this cubic function, which is y equals x cube minus 3x plus 1, then dy by dx is 3x square minus 1. Now it has 2 critical points, x equals plus 1 or minus 1. Now this y at 1, it will be minus 1, and y at minus 1, it will be minus 1 plus 1 will be simply plus 3. Now if we draw an approximate graph for this function, then we'll start from minus infinite, and then we'll take a positive value, and then we'll take a negative value. Now this function, it has 3 real roots. Now, if this function has 3 real roots, then this signum function, it will be discontinuous at 3 points. So in this case, the value of b is simply 3. And it says c is number of points of non-differentiability of this function. Now here we have fx equals log x into mod of x minus 1, x minus 3 plus 2 into x minus 2 to the power 1 by 3. Now this mod function, it is not differentiable at 1 and 3, but at x equal to 1, this log x will be 0. So that means it is differentiable at 1. So it is non-differentiable at 3. And if we differentiate this, we get 1 by 3 and x minus 2 to the power minus 2 by 3. That means it is not differentiable at x equals 2. So value of c is 2. So this function is not differentiable at 2 points. And d is number of points where this graph has a sharp turn. Now it has a sharp turn at 3 because it is not differentiable, but at x equals 2, it actually has a vertical tangent. So in this case, value of d is simply 1. Now we need to find the value of a plus b plus c plus d. Now this is 5 plus 3, 8. So answer to this question is 8. Now the question is, find the left-hand derivative of fx at x equals to k if k is an integer. Now we need to find f dash k negative will be equal to this limit h tends to 0 positive f k minus h minus fk upon minus h. Now this is limit h tends to 0 positive fk minus h will be this greatest real function of k minus h, and then sine will multiply this pi inside, so it will be this sine k pi minus pi h minus, now fk sine k pi is 0 if k is an integer, divided by minus h. Now this is limit h tends to 0. Now greatest new function, it doesn't take a limiting value, it is an exact value. Greatest new function of k minus h is simply k minus 1. And if we look at this sine n pi minus theta, it will be sine theta if n is odd, and it will be minus sine theta if n is even. So basically we can write this as minus 1 to the power n plus 1 into sine theta. So here it will be minus 1 to the power k plus 1 into sine pi h whole divided by minus h. Now this minus 1 will cancel once, will multiply and divide everything with pi. Now this is sine 0 upon 0 form, standard limit 1. So left hand derivative of this function fx at x equals k will be minus 1 to the power k into k minus 1 pi, and that's your option A.